Alright, welcome back to week 7. So this is the beginning of the introduction, really, to calculus and what are the things that we can emphasise. So I wanted to do an informal development just so that you could have a sense of what to do, because we've already learned a great deal about differential calculus. When we put our hands together and make our elbows go to a particular value, or even that one, we get a sense of what the gradients are. Okay, we get a sense of what they are. So we're doing differential calculus all the time anyway. And when you recognise that intuition grows, this is a big step in your development of your support for your integration, your differentiation. So let's do something a bit unfamiliar. Let's take a sine wave. And this is by no means scientific, but what it does is it does highlight an intuitive effect. Okay, an intuitive effect. So if we take little linears, so we go to x at that point, if we blew that up, what would we have? We'd have an x value, and then with the y-axis, and there we'd get a little linear. It'd be so small if we did it'll be a little linear. Just like these guys here, it has a gradient. And as we move along and do others, they too have a little linear. So we can use dominoes or matchsticks or whatever you like. And the idea there is that you can see the change in the gradient. The gradient is changing. And then this way, oh look, it's actually going negative now. And the idea is that when it gets to here, it's maximum negative. And then it's going to get less negative and less negative until we get back to here and we're back to 0 again. And then it starts to increase. And for each one of those, there's a corresponding x value. Okay? A corresponding x value. So the other thing, we could cite this as y equals sine theta or sine x. It doesn't matter how you phrase that. But what I wonder if I could superimpose on that an M curve. I'd really like to draw the gradients. This is a positive, so if I put plus or minus up here, this is the steepest positive, isn't it? So we'd put a point right up here. Okay, and then we'd have less steep, and eventually we get to 0. We get to 0, so we get this less reducing all the way down. And then we've got this one here, this point here, it's maximum steepness in the negative sense. Maximum steepness. And this one here, 0 again, so it's back here. So we're kind of just drawing these points, superimposing what's happening with the, well, that's a bit wobbly, superimposing what's happening with the M curve, as we'll call it. The M curve. Okay, and then it comes back up, doesn't it? And keeps going up to where it's now a maximum positive. And so on and so forth. So this value, the corresponding values, has formed a curve. And this curve is the M curve. In other words, it's the gradient curve. The M curve, or the gradient curve. Or the gradient curve. So we're going to do a formal introduction, but I just wanted to do this kind of informal, right? An informal, just to get a sense of what's happening with the gradient as it changes. And in fact, what we could do is call that y dash, and that's a cos wave. So the function can be sine x. Its differential is cos x. And in fact, we can do that for all types of, curves. So if we take, what are some of the ones we've done? Y equals the ln of x. The ln of x goes like this, doesn't it? Okay, shoots off like that, the ln of x. What else have we got? We could do the one that's hyperbolic. We could see there's asymptote to there, and it goes like that. It's asymptotic. It kind of gets smaller and smaller, the gap, doesn't it? It's got also another quadrangle there. What else we could do? We could do y equals e to the x, and we've studied that one. We've done y equals e to the x. So y equals, 1 over x. And there we know that that can't be 0. So it's asymptotic to that. Y equals e to the x. Okay. So we can come back and do our little linears. And look at this one. This one's always got a positive gradient. It's never less than. Never goes to negative. Forever goes off into positive direction. This one here starts off as a very steep positive. Oh, wow, look at that. Steep negative. It's still negative, but it's just getting less and less and less and less negative. Okay, less and less and less negative. This one here we know is always increasing. The gradient's increasing and getting taller and taller and taller. So if we were to superimpose those, just as an intuitive, empirical way of looking at our curves, we had plus and minus up here. Likewise, we know this one's special because this one here will give us the exact same curve. That's the special one. That's the one that we learned about last week. So we can say that y dash, which is saying the m curve, that's the one we love because that makes our calculations easier. What about these guys here? Very steep negative. Very steep negative, isn't it? So big negative, so that's down here somewhere. And it's just off. The value's just off. Okay. And then it's getting less steep. So it's coming up like this. It's coming up like this. Now, sometimes you're going to get this wrong, and I'm not bothered by that at all because we can check that. Okay? We can check that. But that kind of looks like the ln of x, doesn't it? Look at the shape of that, the ln of x. Okay, we can check all of these using technology. So this one's very steep. It's a very steep positive. Okay, but then it comes down. Okay. Oh, that's like this one, the 1 of x. Oh, look at that, 1 over x. So there might be something to that. Okay, but we'll, so y dash. What's the derivative of the ln of x? What's the derivative of 1 over x? Okay, so these are questions to be answered and asked. So some of the regular ones we're confident, some of the other ones we just pause a little bit, just press pause and say, okay, we think it could be decreasing all the time, or we think it could be increasing all the time. And so the y curve might represent a function that we're familiar with. It might represent a function that we're not familiar with. Okay, so we need to be a little cautious in developing our responses. So we study those independently. All right, so let's have a look at the other thing is that I was going to do some work on the trig stuff, but I've done that enough now. There's enough weeks I've spent on the trig, so if you're doing the trig, that's wonderful. If you haven't done it, you'll reap what you sow in that regard. All right, so last week I did talk a little bit about limits, and I talked about the idea of, there being a personified chair. I had a bit of a personified chair, didn't I? And the chair had one of our chairs with its little feet and things on it. Okay, and then we had a person, and we had a zone, didn't we? And we talked about that distance. And we talked about the idea that the person could be really, really close and close this distance up and be standing so close that for all intents and purposes, they're in the ether. It's a very good analogy in my view. They're in the zone of the chair's space. There you are, protruding in. You don't actually have to touch. You don't actually have to touch. That's not necessary to get into the ew. I think I call it ew. Okay? You don't have to get into the ew zone. You don't actually have to touch. So the limit is when we get into that zone. So for all intents and purposes, not touching. Not touching. For all intents and purposes, touching. Even though we're physically not touching. So physically not touching, but we are touching. Okay, so that's a bit of a trick to work through. So the notion of a limit was that we could approach, and usually what they do at school is approach from above and below. And we look at the limit, and in a way this is kind of a bit porous. The textbooks all over the globe do this. They use a linear one and they say, oh gee, what happens when we get infinitesimally small? And the idea would be that we wouldn't actually take it on. Okay, so as approaches L, but from as approaches A, both ways, from above and from below. As x approaches A, from above and from below, then we can say that the limit exists. So there's a little shortfall in this explanation. Now, this needs to be contrasted with function notation, because function notation says that we actually drop the number in. There you go. Function notation is dropping it in, and so that's how we got to 13. Function notation. But what I want to say to you is, it's not this. It's quite wrong to think that the value takes it on. What it does is approaches this is like an insurance policy. This little thing here says, well, we're going to get within the zone of 6. We're going to get within the zone of 6. And when we get within the zone of 6, for all intents and purposes, we'll have 6. Okay, so the arbitrary assignment of how small we go, there's actually a proof for that. And that's the language of analysis. Okay, and I've raised this with you many times. Analysis, and analysis has sequence. We did that last time, didn't we? And before that we did inequations. So they're kind of the basics of those. So there's actually a subject that you can do called real analysis, which will take you through all of that. Okay, so in function notation, where we've got the graph, we know that we've got our function of x, y equals x. There it is. It's the same thing, just drawn in function notation. Okay, we're not actually doing that. We're not dropping it in. It's very important that you recognise the difference between these two. Yes, there's a similarity in that the number is the same, but there's a conceptual difference that's quite different. So when we drop the 6 in, it actually becomes 6. It actually becomes that value. Students leave school believing this is the case, and it's not. It's not the case. It's not the intention at all. So you have to do some advanced analysis to get that. However, having said that there's a contrast and that they're not equivalent, what we do is we do the mechanics of that. So we actually use, for all intents and purposes, a mechanics of function notation. Oops. So 2 times 8 plus 3 is 16 plus 3, which would be 16 times 2 is 32. Sorry, 4 squared is 16. So 32, here right here. Just fixing that up. It's taking a bit more time. 2 times 16 is equal to 32 plus 3, which will be 35. So the mechanics is that it's kind of being a bit apocryphal, isn't it? It's like saying, well, when we invoke the insurance policy, we only need to be infinitesimally close. And we get the we get the limit. Okay, we get the limit. If we're some way away, then we can use the function notation idea. It doesn't make any difference. So in a way, these linear examples don't really highlight the need for the insurance policy. Why would we need this? Why can't we just use this if that's the case? So we need to explain that. We need to have an understanding of that. All right, so what we're going to do here is we're going to have a look at an example of where the insurance policy helps. So in these are quotients, and so when we're looking at quotients, we're seeing that the denominator has a particular problem. Okay, the denominator cannot be 1 minus 1 because that is 0, and that is undefined. Panic stations. So we can't have an undefined denominator. So we need some kind of insurance policy that will help us understand that we're not going to break the rule. And the way that we will do that is that we will put this algebraic nomenclature in. We will let x approach 1. In fact, we'll let it go so close to 1 that the ew factor kicks in. For all intents and purposes, it will be 1, but in practice, this insurance policy means that this will never happen. Okay, very good. Now, algebraic gymnastics. So x squared, so just taking this up to have a look at this. What is this? Because if I just start writing solutions now, people are going to miss the point, aren't they? So a squared minus b squared is the difference of two squares. It's a binomial product in a and b, and it just means that they're connected with opposite signs. On expansion, that's what you'll get. So this is the same thing. This represents x squared minus, watch, 1 squared. Very common as it turns up. So it's a binomial product in x and 1. And all you've got to do is put a plus minus, and on expansion you'll get that one. So this numerator expands by virtue of the difference of squares. Okay, the difference of two squares. And so I didn't want to suddenly just write the answer, because this is the assumed knowledge that you're supposed to take into Maths 1. What I should have been able to do was just write this bit. I should have been able to skip the previous step and just write x plus 1. And then you would have rightly said, where did the x minus 1 go? So if we'd gone from here to here, you would have rightly said what's going on. There's the assumed knowledge that you'll need in Maths 1. So pull them in together. Algebraic gymnastics. So they will cancel, and you'll be left with x plus 1. So there's our x plus 1. And what happens as x approaches 1? Well, for all intents and purposes, this x becomes a 1. Ew! Not quite 1, but ew to 1. So we'll accept it as 1. And so the limit of this thing is 2. Now you can use technology to check these. So that's another thing that you can validate with. Now, having seen that example, let's be a bit cagey about this. This is a trinomial, so it's a quadratic. What's the chances that x minus 2 is going to be one of the factors? So let's be a bit cheeky, and you can go and do your expansion or your solutions or solve or, complete the square or whatever it is that you want to do. But you know what I'm going to do? I'm going to assume, just for the moment, that x minus 2 is up there. Okay, because I reckon they're going to cancel. So what would go in here? X what? X times x is x squared. The last term would have to be plus 3. So x squared minus 2x plus 3x is a plus x tick, and plus 3 times minus 2 is minus 6, so that's correct. Now, of course, what's happened is this is now the mechanics of doing this. They're cancelling, and we're left with the limit as x approaches 2 of x plus 3. So in this case here, for all intents and purposes, x is going to take on the value of 2, while not actually taking on the value of 2. It's going to be such an infinitesimally small difference that we'll accept it as 2, and so the limit is 5. Okay, so we've got to use the language, we've got to keep the concept alive, because later on, this whole idea of an undefined denominator is very, very important. Okay, so x can't be 2. We did this in the inequalities. X can't be 1 for inequations, and we had some quotient inequations where we learned about the denominator. It's very, very important. All right, so let's think about this in a slightly different way. Let's see if we can come to terms with the idea of a tangential slope. Now, there's a couple of different ways to implement this notion or idea of the secant. This is a secant proof, so it starts off down here at this value, and it starts off up here. And so this line that's drawn through is called a secant between 2 points. and it's a pretty poor representative of a curve. I mean, if the curve was y equals x, it would be great, but it's not. It's this one. So clearly, it's not functioning very well. So how do we get down to that kind of value? How do we get to this picture? See, this picture is quite different. So what's got to happen is that this has to slide down. So in terms of generating an average quotient, we're kind of doing okay, but really it's not that great, is it? It's not really that great, okay, as an explanation. So what we want to consider is how to improve on this. So let's just get through this particular example, because we know this secant, while a bit rusty, doesn't represent this lovely tangent, which is what we like. This lovely tangent, this secant, ooh, phew, it's a little bit terrible, isn't it, in representing the gradient of the quadratic. So let's just explore what we might be able to do at a particular point. We can pick up the values. So we've got some values that we can use and think about rise over run. So we've got some information that we've been given, some value of A, and this is very much an analysis way to do this. I'm going to do something slightly different a little bit to contrast, okay? So we need to work out our points. So we can just put in x equals 8 and we'll learn about the gradient. So function notation, let's put 8 in. What will we get? Well, it turns out we'll get 55. So if we put the point in 8 to 55, and we could need another one. Well, we've got 2. We could put y2 in. So what would be y2? Just take it off the graph because it's there at 2. It's clear that it's 2. And so the value will be 7. So we've got 2 and 7. So we've got 2 and 7 and 8 and 55, just by way of an example for these. So let's work out the gradient, as it were, through the secant. What's the gradient of the secant through those 2 points? So we would take the first point, the y of 0.1, minus the y of 0.0 over so that's the rise, and the run of 0.1 minus the run of 0.0. Okay, so let's not take our eyes off the prize. Rise over run. I know. 55 minus 7 over 8 minus 2 is 48 over 6. And so we get an average gradient. What is this gradient? What does it actually mean, the gradient of a secant? It's kind of a poor cousin, okay? And that's got a linear line, isn't it? So we've got 2, 7 and 8, 5. Now at this point you should be able to build this up and find out what the line is, because that's a Pearson proposition. Y secant equals mx plus b. Well, we just worked out this value of m. We said it was 8. And so I'll leave the rest here. We're going to do another couple of examples later, but we're getting distracted from what is it about. How do we go from secants down? So we're going to test a few values, okay? So if we move the point, this one, 855, if we move it down and pick some more points, so there's 631 now, there's 415, so we're moving this down, and look at what we're looking to do here. We're moving it down, and what's happening to the gradient? The gradient's getting less and less. That's just happening because of this example. So the gradient 8 is 6 and 4, so there's our point, okay? And the line, we're given the line equation as well, okay? Our gradient, we've already just worked that out, okay? P1 minus PO, rise over run. We're not afraid of that at all, because that's something we're used to doing, okay? But it takes on the function values, and it's doing it generically with I and 0. So the function values are going to have these generic. This is like a general expression. In some ways, probably not very helpful, but it just imprints the idea that this analysis can be done this way. But I'm going to change it a little bit. So, as x is getting closer to 2, there it is, coming down to 2. Down you come, down towards 2. PI is getting closer to the tangent to the curve, and this is the grace of the thing. It really wants to know what that tangent to the curve is, and that's this one, tangent to the curve. The secant has become tangent at that point. Okay? So we can do this analysis through the eyes of a limit. And so I think what I would like to do is just pause there. Okay, I would like to pause there because I want to bring this back to a new idea. So I'm going to redo all of this, and I'm going to redo it up on this sheet up here. We had a blank sheet up here somewhere. And so, where is it? Here we go. All right, so we've got our secant curve. We've got a quadratic that's sitting like this. We had a point here somewhere and a point here, and we had our values going up like our secant. And so across here we had some value of x, so a function value of x, function notation. And up here we have this value, which is now something we'll just consider for the moment. And down here we have another value. So I'm going to express this as some value x added a distance h. So I'm going to call that h, big H. So this is going to be x plus h. So this function value is x plus h. Okay. So all we're going to do is consider the rise over the run. So the gradient for this secant is going to be the rise over the run, which is going to be the bigger value, subtract the lesser value. Okay, that's just positive x, over the bigger value minus the lesser value. Oh, that's a funny result. They go, and so we're left with the function value, the bigger function value, where h is bigger, minus f of x over h. So h is quite big here, isn't it? So if we just change colour and slide the secant down a little bit, we'll slide it down here, and what happens to h? It's still there, but it's a bit smaller. That's that value there, x plus h. And look at the secant gradient has changed, just as it did in the previous example. Okay? What happens if we keep going with this idea? So we'll slide down the secant a bit more, and so this h now will be a little bit smaller. This point here will still be x plus h. So our equation hasn't changed. We're still on track to make the gradient of the secant. Okay, very good. So let's push it down a little bit further. Okay, let's push it down a little bit further. So this time, I'm going to bring it down to here. Oh, now h is really small. H is really small, and this is still x plus this little h. Wow. Okay, and the gradient is going off like that. Very good. Okay. Still everything's okay here, no problem. All right, and in the final one, let's drop it all the way down. Let's drop it all the way down here and put the orange one there. So the orange one is the tangent of the secant. And what's the distance? H has become 0. Now wait a minute, there's a problem. H has become 0. For our orange one, we're dividing by 0. Undefined. This is no good. So this is what's happening. So one of the great and profound ideas happened. The creators of this concept said, well, let's take out an insurance policy. Let's modify this. so that as this point drops down and comes over the top of this one, we effectively say, for all intents and purposes, h approaches 0. So that means that in our explanation, we're never going to become undefined because h never becomes 0. So this was one of the great moments in mathematical history for differential calculus. H never becomes 0. Okay? So we can do an application of this. So let's do an application of this. Okay? Let's do y is equal to x squared. So the gradient is going to be the rise, first principles, minus x over h. Well, we're going to put the insurance policy in. And the important insurance policy says h yield gets very close to 0, but never actually becomes 0. So everywhere there's an x, we'll put an h in. So we get the limit. So you always have to write your insurance policy because it tells you what won't happen. So we'll put x plus h in brackets. Then f of x is just x squared. We've got our h underneath. Very good. Now you'll see that this is a perfect square. So the limit of h approaching 0, we do an expansion, x squared, 2xh, h squared. So that's our shortcut for quadratics. So if you didn't do quadratics, this is a puzzle. Now we'll notice that there's a positive orange and a negative orange. So they're gone. So we're left with the limit of h approaching 0. H approaching 0 for 2xh plus h squared. Now what do you notice? On the denominator, there's terms connected by pluses. So that allows us, yes, I'm sorry, the insurance policy's got it written every time, to take out what's common across there. In this case, it's h. So we're left with 2x on expansion plus h, and now we've got a product, and they can cancel. So we're left with the limit as h approaches 0 for 2x plus h. Now h, for all intents and purposes, is going to become 0. It's going to be infinitesimally close to 0. So for all intents and purposes, we're left with 2x. Okay? So y dash, or m, is equal to 2x. So there. Now we did that with code 1, if you recall. Code 1 was a thing we did in algebraic gymnastics. So some of the rules will show us quite readily how to do that, and we'll see those in a minute. But I just thought I'd insert that because I think that's an important long step development. And we can do the quadratic that was done previously in exactly the same way. Alright, so for the purpose of completing what we just started, which I pressed pause on, let's have a look at it through the lens of analysis limits as it's applied this way. Now this makes it a little bit difficult because x is going to approach xo, so our insurance policy is expressing it just a little bit different. It is approaching our xo, which is where we get our function. So we get our f of x minus our f of xo, so it's expressed slightly differently. Still rise over the run with an insurance policy, but nevertheless, it does look a little bit different, doesn't it? So we include the insurance policy. So x this time is going to approach 2. We've got x squared minus 2x plus 7 minus 7, and that is f at 2. So it's a little bit different, this technique. Okay, over x minus 2. And so we get the limit as x approaches 2 for Now, the 7's will cancel, plus 7 and minus 7. So we get x squared minus 2x over x minus 2. We can clearly see that's going to be a common factor. So we'll take that out and put a bracket in. And we can see now that x minus 2 will cancel. So off you go. And so we're left with the limit, our insurance policy, as x approaches 2 for x. So that becomes, for all intents and purposes, it's going to become 2. Okay, so we've got the gradient at the tangent at the point x equals 2. So we've got one coordinate x equals 2, and if we put 2 into there as a function notation, we will get 2 2's are 4, minus 4, we will be left with 7, which is what we anticipated from our diagram. So we're able to develop these limit ideas a couple of different approaches, but that's why I put this one up, because this one is very much what happens at school. This one here is very much what you would be tested in year 11 at school. So that first principles applications. Okay. All right. So the next thing we'll consider is if we replace 2 by a general value. So instead of having to work through that by any other value, and we'll just call it A. So we want to generalize that example. Okay. Then we can use this. Now, I'm not saying that we're going to be doing this. I'm not a particularly big fan of this way, but it's here for completeness sake. All right, so if we insert the example here, and suggest perhaps that we do it that way. So the limit as x approaches some value of a for x squared minus 2x plus 7. That's our f of x, rise over run, a squared minus 2a plus 7 over x minus a. Now clearly here our insurance policy shows you that if x is a, that's 0. So that's a fail, but it's not, because we've put insurance policy. Okay, so that's how we're dealing with that. So we're doing the expansion on all of these and grouping in pairs where we can. So a little bit of algebraic gymnastics. So we get x squared minus a squared minus 2 lots of x minus a over x minus a. This is the difference of squares, so just more gymnastics. I think the gymnastics takes away sometimes, doesn't it? Okay, so we've got the difference of squares in x and a. That's easy. Minus 2x plus a over x minus a. Okay, now we're still not able to do any cancelling because of this, so we need to be careful there at this point. So the limit of x approaching a, so we can see that x minus a is a common factor. Sorry, that's a minus. I might just fix that. X minus a is here and here over this minus sign. So x minus a can come out as a common factor, and we're left with x plus a and minus 2. So that's this bit. So the common factors come out, and we've got an x minus a, and look what's happened. They've cancelled. So we've got our limit as x approaches a for x plus a minus 2. And so we end up with, for all intents and purposes, x is becoming a. So we've got a plus a, which is 2a, minus 2. And this represents the tangent at 2. It's algebraic, yes. So it represents, as a function of x, the tangent will be 2x minus 2. Now we can start putting values in here, and we'll get numbers for our gradient at some value of x. So there's a way to do it that way. So there's a couple of different approaches with analysis, but don't fret them. They're here for your education, and I'll point out when it's important to do that. So these are interchangeable symbols, M, Y dash, don't forget DDX, okay, and then if we change the pronumerals around and say S dash of T or DS DT, the principles don't change, S dash, okay, or DDS, DDT, all of these would mean the same thing, okay? So just keep in mind that when we get a change of pronumeral, it doesn't change anything. All right. So what we'll do is we'll pause the video there. It's gotten away from us a little bit. That's at 40 minutes. So I'll stop that one and we will come back and continue on. Thanks.